Hello everyone, welcome to Chapter 6, the normal distribution. We are still in the continuous probability density function topic, and we saw previously a specific case of it was uniform distribution. And here we talk about normal distribution. This is the most widely used distribution in statistics, and therefore it is really important. To simply put it, this is related to the bell-shaped graph that we've been speaking a lot about. So a normal distribution has a bell-shaped graph. This is generally how it looks like a bell, so we say bell-shaped graph, but it's also known as the Gaussian curve. And that's in honor of Carl Friedrich Gauss, a mathematician who played an important role in the discovery of normal distribution. And this bell-shaped curve is used in almost all disciplines. Therefore, it's very, very highly utilized. And if I shade this area here, right? Remember, it's a continuous probability distribution. Therefore, you will be shading the area in order to find the probability. And so I can say that the probability is the total area under the curve, which is 1. And always remember, 1 is the same as 100%. Now we can have different kinds of distributions, bell-shaped curves. So let's say, you can have a tall and skinny one. You can have something more spread out and, not much of a bias there. Skewness there. I said bias. Skewness there. And something as flat as that is also fine. So what we're seeing here is, do we have these graphs that are, normal distribution? Are they bell-shaped? And they look very different, right? And what's really the standout feature is the peak of the graph. And it is important because the peak of the graph is where the center is, the mean. Okay? The center or the mean is at the peak of the graph. So what you can see is, if I draw the line through the peaks, you see that they're not lining up, they're not the same point, right? Because these are different distributions, they can have different peaks at different points. And because of that, we really like to standardize them, so that when we standardize each one of these graphs, it's like putting them on a new scale. When we standardize them, they will all be like this, where the center is always I have to remove that. The center is always a 0. So the mean is 0 and the standard deviation is 1. So this is what the standardization does, where it gives all the standardized distributions the same mean, 0, and same standard deviation 1. So when you standardize, what we do is we move from this X scale to a Z scale. Right? Because think of it again like Celsius and Fahrenheit. Okay, so in the eastern parts of the world, they measure temperature mostly by Celsius. Here in the western part, we use Fahrenheit. So if you are talking about world weather conditions, it's going to be confusing to have some in Fahrenheit and some in Celsius, and to constantly keep reminding the research group or the audience or wherever you are presenting this information that you have two different scales. So by standardizing or bringing them all to the same scale, you are able to talk about all of them in a more general sense, and therefore the point you're trying to make will be a lot more cohesive. So then what you'll do is you'll convert all your Celsius into their corresponding Fahrenheit temperatures, so that when you are presenting it, They're all in Fahrenheit, and so your information is translated or understood much better because of the standardized version. And, you know, once you have done all your study or your research or even presented your case, then if the audience wants it in Celsius, you can always convert it back to Celsius and give it to them, right? That's the same idea here. So we have our bell-shaped curve all over the place, in the sense their mean can be in different places. And so by bringing them in the standardized form, by switching all the x scale graphs to a z-scale graph, you are making them all standardized and making it meaningful, just because you now have no worry about having a different mean or a different standard deviation. Is always standard. And what's more, your bell shape is preserved. You are just switching from x scale to z scale. Okay. That's a general idea, but let's go ahead and look at the parameters, you know, the characteristics of normal distribution. Now, in our uniform distribution, we said x follows, or the squiggly, u of a comma b, because a and b were the parameters, they were the big players. The formulas, everything involved that. Now, for normal distribution, we will say x follows a normal distribution with mean mu and standard deviation sigma. Mu and sigma are the key parameters for normal distribution. So if you had mu and sigma, you can basically do all these calculations. So probability of x, like we had the binomial distribution, right? We had the formula ncx p power x 1 minus p power n minus x. And for uniform distribution, it was very straightforward because it was just the area of a rectangle. But here, remember, you're drawing this bell shape. So this curve has to be mathematically a function. And so we do have the density of the normal distribution coming up as a complex expression. And it looks like this. 2 sigma squared. Obviously, you do see the mu and the sigma playing here, and of course the x, because that's a random variable that you will need in your calculations. And you know pi is approximately 3.14, you're familiar with that. And E is the natural base, so E is also an irrational number, which is approximately 2.7. So we have, these are irrational numbers. Your calculator has them inbuilt. So they are not variables, you know, they are basically numbers in the background. So your variables, things that can vary in this, is that you have x, the mu, and the sigma, and depending on the problem, those will change. So what are the features of normal distribution? The most striking feature is that they're symmetric, the graph I mean, right, is symmetric around their mean. And then we have the mean. That's the spectacular part. The mean, the median, and the mode, they all coincide. They're all equal in a normal distribution. That's fantastic, isn't it? That's why it's more sought after, because we have done exercises where the mean, median, and mode gave us different values. But here they all come together. They're all equal. Okay? And then we saw already that the area under the normal curve meaning the bell curve, is 1. And the normal distributions are, you know, they're denser in the center because you have more values, more values around the center. And towards the tail, it kind of tapers and it's less dense in the tails. So I'll just say denser in the center. Less dense in the tails. And of course the two parameters are mu and sigma. These are the parameters, the characteristics of this distribution. And what you'll see is, in fact, because of the symmetry, right, you can divide it out like this. You can say, well, this is your mean, right? So I'll just say mean. So this is, if you went one standard deviation, mu plus sigma, okay? If you added one standard deviation to the right of mu and to the left of mu, so that's mu minus sigma, you will have this whole distribution, right? This middle chunk basically. If you went one standard deviation to the left and to the right of mu, this will account for 68% of all the data values. Okay, all the data values will lie within one standard deviation from the mean. And if you went two standard deviations, that means mu plus 2 sigma, because you went 2 sigma units, and this is mu minus 2 sigma. So this is going to bleed into each other, the colors. But I want you to see this whole thing, the blue and the greenish area, because of the yellow part. This whole thing will account for 95% of the area. You already have the 68%, but if you went two standard deviations, you're getting 95% of the area, which means you have 95% of all the data values within two standard deviations. More than two standard deviations means that, you know, it's a little unusual, because meaning it in the sense that it's significant, because most of your data is lying there, and you'll have you know, only ones that are really far off from the mean will end up more than two standard deviations away. So if your distribution is so basically you do not want your distribution to be too spread out, right? If you have two spread out values, that means your values are varying much. The variability is high. If it varies much, then you know, it's not really hovering around the center, therefore rendering it to be more vulnerable to change, or more making it unreliable, or less reliable, I should say. So more spread of the data means less reliability. If there is less spread of the data, that means we will have a more robust distribution. So in other words, the spread of the data, or how widely spread it is, like graphically, it just means that we're talking about the standard deviation. So so if I gave you, let's say, 3 graphs, okay, and let's say that went like that. So you have 3 graphs, and what you notice is, for graphs that have more spread, they will be short and flat because they're spread out. Okay? So among the 3, which one is the shortest and the flattest? Of course, it's the green, right? This one is short and spread out. That means the standard deviation is high. High deviation, because the deviation is deviated from the center, right? On the other hand, if it is tall and skinny, it implies that the standard deviation is low. Okay, small standard deviation just means that you have less distributions or less spread. Okay? So please remember that if the standard deviation is low, it just means that most of your data values are clustering around the center, which is desirable, because they didn't really get spread out too much. Okay. All right, and then we were talking about the standardization, right? Standardization, how do we convert from the X scale to the Z scale? As I mentioned, X scale, the problem with X scale is that your normal distributions can have all kinds of means different means, different values, right? So your mean could be 10,000 tons, or it could be 0.05 millimeters when it say if you're measuring something that's really small, or it could be 7 hours. So it gives us different values, and gives us in different denominations, right? Different units. But when we standardize it, all those things are eliminated, and all we have is from an x scale that is normal mu comma sigma, you convert to a z-score, okay? So these are called x values on the x scale, and z, this is also normally distributed, right? But then your mu is fixed to be 0, and the standard deviation is fixed to be 1. So that is really spectacular, and this will be on the, this is called the z-score. That's called the x value, this is called the z-score on the z-scale. Okay, and that's the standardization that we really look for. And when we do the standardization, here is the formula. Z is, so you have uppercase z to indicate the variable, random variable, but the values themselves will be lowercase z. So I want to just use cursive z so you can differentiate between the two. So the lowercase z is x minus mu over sigma. That's it. You do this formula and you can switch from x scale to z scale. Okay. And again, if you rearrange these terms, you can always move back from the z scale to x scale. Okay. So this would be from x scale to z score. Now if you wanted everything in terms of x, that will be mu plus z sigma. This will help you to convert from z score to the x scale. And that can happen, right? When you say you're given something z value, you can use that to go back and explain in terms of the original context of the problem. So if you have it in minutes or centimeters or inches or tons or whatever your measurement may be, you can bring it all to z, do all your calculations, because there are some advantages to that which we'll look at shortly, and then translate your answer back to the context in which you were originally asked to answer that problem. And so it's just a way, a crutch to help you get past a situation. Okay. Now let's do some problems to kind of check this out. Now when we try to translate from an x scale to a z scale, we realize that the axes will also slightly differ, right? So this example will illustrate that. Suppose x follows a normal distribution with mean 17 and sigma 6, right? 17, 6, and x equals 5. Find and interpret the x score of the standardized normal random variable. Okay, so x is 17 and 6. So then we have mu to be 17, sigma to be 6, and we're also given x equals 5. We need these three things. Okay. So now z is, I should use the lowercase like this so you can see the difference. It will be x minus mu over sigma, right? So that will be 5 minus 17 over 6. So if you did the calculation here, that will be negative 2, right? Yeah. Negative 12 over 6, negative 2. So what does this mean, this negative 2? Now I want to just show the scale here, the scale difference that takes place here. So let's say this is the x scale. Okay. So what this says is my normal distribution looks like this, and okay, the mean is 17 and the sigma is given to be 6. Okay, so we are looking at x equals 5. So mean is mu 17. So think of x scale as the number line, right? So this is centered at 17. So 5 is somewhere here. 5 is a value somewhere here. Okay. Trying to find the probability, or at this time we're not talking about probability, we're just trying to find the location of 5 on the bell curve on the x scale. Now what we do when we translate is, we now get the same bell curve, it's supposed to look alike. Okay. Let me the reason I put that again was I'm trying to stretch that mean because they have to match. But remember, this is my z scale, so the mean will be always 0 and the sigma will be fixed at 1. So what we're saying is this value 5 corresponds to -2 on the z scale. So they're asking, what does it mean? What does this -2 mean? When I look at 5 and 17, I can't see what it means very clearly. But on the z scale, I can see that -2 and mu equals 0 tells me that from the mean, we are 2 standard deviations away on the left or below, right? If you think of below or to the left. And that is very important because we previously established that if your data values, let me take you back here quickly. If your data values are 2 standard deviations away from the mean, then you have 95% of data falling in there. Now all those details will become meaningful in a z-score, in a z-table, as opposed to the x-scale, because that is raw data. When you convert it, this makes more sense, because the standard deviation 6 there would have us a little thrown off. But basically what we're trying to show is that this conversion really helped us to arrive at that 5 corresponds to -2 here. So x equals 5 corresponds to z equals -2. And also what's striking about the -2 is the negative value automatically tells you that it's on the left of the mean, right? On the other hand, on the x scale, you couldn't tell that because 5 and 17 both are positive. So you really can't tell unless you realize, well, mu, the curve is centered at 17, therefore 5 is to the left of it, so it's kind of negative implication there. So the z-scale puts things the way it is. If it is -2, you know it's -2 on the left, meaning 2 standard deviations from the mean on the left. If your z-score came out to be, 3, that means it's 3 standard deviations on the right. If it was -1.7, then it's -1.7 standard deviations to the left of the mean. So you can make all these things meaningful in the z-scale. So they wanted us to interpret this, so let me go ahead and interpret it. Okay. So x equals 5 is 2 standard deviations that is 2 sigma. And remember, 2 sigma is 2 times sigma, so sigma is 1 here, therefore 2 times 1 is 2 itself. That's why you can exactly say that value itself is that many standard deviations. So 2 sigma below or to the left of the mean mu equals 17. Right? You know that it's, when you position things, 5 is to the left of 17. But how far is it from 17? That information comes from the standard deviation. So when you measure in terms of standard deviation, that makes perfect sense, especially here, because the standard deviation is 6 when you talk about the x scale. Okay? So let's test it. Okay? So now your 2 standard deviations is 6 times 2, right? Because 6 is the standard deviation. The sigma is 6 for the blue, for the x scale. So 6 times 2 would be 12. Okay. And if you look at the distance between 17 and 12, okay, so distance between mu and 2 sigma is 17 minus 12, which is 5. That's why it is sitting at 5 on the x value. Okay. So all that becomes, again, as I mentioned before, apparent in a z-scale as opposed to an x-scale. Here we go. Angelica is a tennis player who averages 6 aces every game with a standard deviation of 2. Suppose the number of aces she gets every game is normally distributed, and let x be the number of aces per game. Then x is normally distributed with 6, 2. Suppose Angelica only gets 2 aces in her game. Find and interpret the z-score. Okay, so now let's collect the information we have. This is given to us. If not, we could still build it because average is 6 aces. That means that's the mean. With a standard deviation of 2, they made that very, very specific. Standard deviation, so can't miss that. And x represents the number of aces per game. So they want us to find the z-score when Angelica gets only 2 aces. So when the number of aces is 2, what happens? So x is 2, mu is 6, and sigma is 2. So your z conversion says z is x minus mu over sigma, which is 2 minus 6 over 2. Okay, it's getting a little boring because we're getting back a -2. Okay, -4 over 2 is -2. Okay, it's boring because we just interpreted this. But anyways, the idea here is that x equals 2 is 2 standard deviations to the left of the mean. Is 2 standard deviations to the left of the mean. Now, we understand that z-score is meant to be neutral, right? So it really doesn't tell us anything other than how the distribution is from the mean and how many standard deviations. So if they gave us everything in z-score, how does it mean? What does it mean in the context, right? So that's this problem. The z-score of 4 tells us that x equals -3 is 4 standard deviations to the right of the mean. The standard deviation is 2.5. What is the mean? Oh. So they're basically asking us for the mean as in the mu, because what we have is the z-score. So they're asking us what the mean is. They gave us sigma to be 2.5, x is -3, and z-score is 4, right? So if you recall, we had this x minus mu over sigma was when you went from x to z. When you want to go from z to x, then we use this mu plus z sigma. This is from z to x. So we're going to choose this one to work on. Okay. So when you have, and by the way, you're not trying to find x, you're actually trying to find mu, right? Mu is missing. So x would be -3. Mu will be mu itself because we're trying to find that. Z-score was given to be 4. And sigma is given to be 2.5. So this is a mathematical case, so go ahead and simplify this. So -3 equals mu plus 10. And then subtract 10 on both sides. You get mu equals -13. So we found mu to be a value for that context. They didn't give us the context, but we were able to use the z to x conversion to get mu. Now in this problem, Barbara scores 3 goals on average for every soccer game. Suppose Barbara scores 5 goals in a game and this value has a z-score of half. What is the standard deviation? Interesting, because here again, in the previous problem we found the mean. Here they're asking us to find the standard deviation. So let's go backwards. So standard deviation, sigma, is asked. Z-score, very explicitly given to be half. And Barbara scores 3 goals on an average. Okay, that tells us that mu is 3. And Barbara scores 5 goals in a game. So this is a specific instance. That means it's a random variable value when x is 5. So we got all these players, and we know we want to get sigma because z-score is given to us. So you're going from let me take you back here quickly. So you're going from z to x. Okay, you're given z and you're trying to find in the x mode. So x equals mu plus z sigma. X is 5. Mu at this time is given to be 3. Z is a half, but sigma is unknown. Okay, subtract 3 on both sides, you get 2 equals half sigma. Then multiply by 2 on both sides, which means z equals 4. Sigma equals 4. So sigma is found to be 4 in this particular problem, where they gave us a context, right? So Barbara scores 3 goals on an average with 4 as the standard deviation. Now I'd like to show some problems using the graphing calculator, and I also like to show some using a manual way of doing things, so that you can understand the background that works in the calculator. So we know that the bell curve on an x scale has mean, mu, I'll just say mu, okay, mean, mu, and these are the positions, mu plus sigma, mu plus sigma, 1 standard deviation, mu plus 2 sigma, 2 standard deviations. On the right, this is 1 standard deviation on the left, and 2 standard deviations on the left. You can go up to 3 actually, because most of them are covered by the time we reach 3. So in other words, this is your x scale. So your x scale goes towards negative infinity on the right, and on the left and on the right it goes all the way up to infinity. So technically your graph actually tapers close to the x-axis 0. So you definitely have most of your data values kind of covering between these 3 standard deviations. Okay. Now having this idea will help you to understand what happens in the background of your calculator. Okay. So I'll do a problem showing manually how to do it, and then we'll do it on the calculator. Okay. A random variable x records a randomly selected score on a test where the distribution for the score is normal with mean 20 and standard deviation 5. Find the probability p of 15 less than x less than 30. Okay, let's look for some clues here. So the distribution is given to be normal with mean 20 and standard deviation 5. They're asking us to find the probability. Okay, think again. For uniform distribution too, when they asked us to find the probability, because of the continuous random variable, because of that nature, it was always a shaded region. We didn't really count it or use a table. We instead use the area to find the probability. So keep that in mind, and let's write this crisply as x follows a normal distribution with mean 20 and standard deviation 5, 20, 5. So we got that. And because it's a normal distribution, we know it's going to be bell-shaped. That's the family. Right? And then this would be the mean, and standard deviation is 5. Okay. Now they're asking us to find the probability between 15 and 30. So if you come back here, you can see that if it's between 15 and 30, you can think of 15 right here and 30 right here. I'm just approximately marking 15 and 30 because it's a number line. So we're trying to find the probability between 15 and 30 for this one. Okay, this is the shaded region that we're trying to find the probability for. Now previously, for the uniform distribution, we were able to use the area of a rectangle because of the shape, but here you can't use that. So we have to do it in a different manner. And I'm going to show it to you first manually how we do it. So I'm going to convert this to a little over. I'm going to convert this to a z-score. That's better. And the conversion does, what it does is it maintains the same shape, It maintains the same positions, but now I've moved to a z scale. This was an x scale. And you know how z scale helps standardize these things. If you go to a z scale, you automatically have mean as 0 and sigma as 1, right? Now because I adjusted the mean from a 20 to a 0 and the sigma to from a 5 to a 1, you know that these ones also will correspond here, but now I'll have to find their corresponding z-scores. Because there are two values, I'm going to call this z1 and I'm going to call this z2. Okay? And notice again, it's the same area. Again, they should look identical, the shapes I've tried. Okay, you know my skills now. So this is the best I could do, but I hope you understand that I'm trying to draw the identical curve. So it's all the same region, you're just doing it on a different scale. Alright, so for z1, I'm going to do it this side. z1 is x1 minus mu over sigma, because I'm going to call this as x1, because we have two endpoints, right? So that will be 15 minus 20 over 5. Compute that, okay? So that's going to be negative 5 over 5, which is negative 1. So my z1, this position here, right? So let me use a different color. This position here is 1, negative 1, I mean. Okay. Let's come over this side, okay? z2 would be x2 minus mu over sigma. I'm just improvising the formula to write x1 and x2 to indicate two different values. So that's going to be 20 minus 20 over, I apologize, I marked the wrong one, it's a 30. 30 minus 20 over 5, which is 10 over 5, which is a 2. So if you come over here, this z value here will be z equals 2. That's a negative 1 that side and a 2 this side. Now the reason we do this z conversion is, before the onslaught of all the technology here, scientists and statisticians used tables. So they used z tables particularly. These were painstakingly derived by statisticians. So they came up with this table. This also is actually a modern table, because you see that it's got 5 decimal places. The traditional one actually has only 4 decimal places. It was calculated for up to 4 decimal places. So I'm going to use this one for the sake of this example here. So we have negative z score table. So you can see here this column shows negative z, and the body of the table corresponds to the probability. So this table gives you the answer right away. It gives you the area. So they've computed the area for us. We may not find the exact value sometimes, but it's definitely tried to be exhaustive of all the values we have. So what this does is, as you can see in this graph here, this is taking all the area from the leftmost end. Okay, so we call it the cumulative area, like how we did the binomial PDF and binomial CDF, where CDF was a cumulative. Here we have it cumulative from the left. So there too it was from the left, right? You add them all from the left. So this by default gives you the area from the left. If you wanted area from the right, like previously, we have to do the complement rule and do 1 minus the left to get the right, because the table directly does not give you the right. It gives you only from the left. Okay? All right. And then we have the negative z-score table. We also have a positive z-score table. Okay? So this has positive z values. And you know that is true because we have the positive and the negative values for z, because it will be on either sides of your mean mu, which is 0. Okay? So coming over here for us in our problem, way off, I guess. Here we are. All right, I know it's a little cluttered, but what you can see here is we are asked to find the probability of 15 less than x less than 20, right? Let me take you back to the problem. 15 less than x less than 30, that's right, not 20. Which is correspondingly, that 15 here corresponds to the negative 1 here. So on the z scale, so negative 1, so the z values are between negative 1 and 2. So I say Well, the x scale is now converted to the z scale of -1 because that corresponds to 15 and 2 which corresponds to 30. Now this is an area that's trapped between two z values, right? And if you look at the table is only the cumulative area from the left. It's not giving us any area in between. So if I want the area from the left, I have to do a little manipulation. So what we do here is we try to understand that this area, I'll just draw maybe a graph here to kind of illustrate this. When I say z score is -1, and if I use the table, this is the area that I will get. Okay, let me use a different color because we already used that. This is the area I will get, right? Cumulative from the left. So the body of the table will give me the blue shaded region. And if I use the table to find the value, not -2, +2, for z +2, I will have this region all the way from below -1 up to here. Okay, I'm sorry that it's the blue changed color, but it's good in a way, because what we see here is if I measure, or if I use the table, I get the area to the left of -1 and the area to the left of 2. But what I'm really interested is in this pink area. So I need to eliminate this blue area. So for that, what we do is we do the probability of x less than 2 from the table, or not x, z less than 2, minus probability of z less than -1, right? Because it's going less than means to the left of. So to the left of. So then if I took my table value here and went to z equals 2, because that's the larger area, right? Because it's on the right. So z equals 2 is the larger area. So larger area minus the smaller area gives me the pink, just the pink part without the blue. That's the desired portion between -1 and 2. So let's go over here. Z equals 2 is a positive value, so go to the positive table. And z equals 2 is here. It's exactly, oops, it's a 0.2. Z equals 2 is exactly here, and it's an exact value. So it is like z equals 2.0. So this is it, because we need a table value. So we need to correspond it to the 0 up here. Okay. So 2.0 basically is 0.97725. Minus z is less than -1. So let's go to the negative table. -1. Here again, -1 is an exact value. So we go against the 0, -1.0. And that table value is 0.15866. Use your calculator and take the difference. That gives me 0.818594674. Okay, and so we can always round it. We always like to give it up to, I don't know, 4 decimal places. So we can kind of box it here. So the probability of x lying between 15 and 30 is 81.86%. So 0.8186 or 81.86%, right? So we did this manually by getting the shaded region using the table in a traditional manner. Now if we were to do this on the calculator, that will be super easy. Okay. Now we have again normal PDF and normal CDF. So I'd like you to go to second vars. That's the distribution. So for all these distributions, binomial, Poisson, normal distribution, we have to use the second vars distribution. So there you have 2 tabs, distra and draw. So stay on the distribution tab, And there, right there, the first one is normal PDF. This is when x is exactly equal to a value, you'll use PDF. And that's the first option. And then you have the second option, which says normal CDF. Now, with the normal PDF, if you choose that, you will only have one x value to enter, okay? But if you choose normal CDF, you'll have a range, 2 values to enter. So right there, you'll know that you have to use the normal CDF. So let's go to normal CDF, which is the option number 2. And when you hit that button, you get hold on. I'll just say enter. It gives you a fresh screen that looks like this, right? Normal CDF. Again, let me mention that this is TI-84 Plus, so it opens into a new screen. I've seen some other calculators that just ask you to enter or plug in these values. You'll have to enter the lower value, the upper value, mu. So I'm just going to write that here and just check your own, the manual or the tutorial that comes with your calculator to see if they match. Okay. So for the lower limit and the upper limit, so you come back here. Remember, this is normal CDF, not the standard normal. That standard normal would be Z. Normal would be just the X. So you go to the X scale and you basically actually stay in your problem, and the lower value will be 15 and the upper value will be 30. Okay. So lower value is 15. Upper is 30. And then you have mu, it's automatically at 0, so clear that or just type over it, and again go back to your question and locate your mean. The mean was given to be 20, standard deviation is 5, so mu is 20 and sigma is 5. And then hit paste, and then it opens up for you as normal CDF 15, 30, 20, 5. And this is what I meant by other calculators asking you to punch in these numbers in the parentheses. So anyways, then hit enter and you get the answer as 0.8185946784. Because it's a calculator, it's able to get that calculation, that area measured, calculated more accurately, so it's giving us more decimal places. Nevertheless, let's round it and you get the same answer in an instant. You basically got it in an instant. And what more, you did not translate it to the Z scale. You kept it in the way it was given in the problem on the X scale, and you got it and got to use those values directly. Okay, so there's definitely an advantage in using the calculator, but I wanted you to see the background working that led us to this. So just because we have the calculator does not mean we're going to do really well, because we should really know what it means or how we are plugging in these values and what results they mean. So here the whole idea of this 0.8186 is that you are looking at an area in the middle around the mean, so that was 1 standard deviation on the left and 2 standard deviations on the right. I'm able to say this because of my z-score. Z-score was -1, which means 1 standard deviation on the left, and z equals 2 was 2 standard deviations on the right. Again, the drawing that I have here may not justify it, just because I should have gone a lot more, but I just did a rough estimate of positioning 15 and the 30. But what we see here is that the z-scores really tell us, oh, you should have adjusted your graph some more, because you need to give more room to accommodate nearly 80% of your area, right? All right, so that was an example where I showed you both manually and by using the calculator. The random variable x records a randomly selected score on a test, where the distribution for the score is normal with mean 75 and standard deviation 15. Find the probability of x lying between 80 and 90. Okay, x is normal mean 75 and standard deviation 15. We're asked to find probability of 80 less than x less than 90. We're going to do this using the calculator so we get the answer quickly. However, we don't want to skip out on what we would have done if we were to do manually, right? So they're saying that this is mu is 75, sigma is 15, and between 80 and 90, so that's to the right of 75, so that's somewhere here, I don't know, 80, say 80, and then I'm just eyeballing this to some value there, and we're trying to find the area between these two, right? And so if we were to do this manually, we would go further and get a corresponding z-score and then find the corresponding 80 mark and the 90 mark, and oops, same shaded region, but here mu is 0, sigma is 1, and we'll have to find the z values for z1 and z2. Okay, z1 and z2, right? So we're going to use the calculator now, so go ahead and go to second vars, which is your distribution, and because it's not one specific value, it's a range of values, you go to dist and second normal CDF. And there your lower will be 80. If you have the previous entries in there, you'll have to of course clear it. And upper will be 90. Clear your mean. Your mean is mu is where are we? 75, and sigma is 15. Hit paste. So that gives us 0.2107861441. Again, round it to, this is the probability, right? So then I'll just write the final answer. 80 less than x less than 90 is approximately 0.2108. Okay. Suppose the heights of high school age males are normally distributed with a mean of 72 inches and standard deviation of 4.5 inches. Find the probability that a high school male is shorter than 64 inches. Okay. X is normal with 72,4.5. Okay. The graph always helps. I know your calculator is going to give you the answer right away, but please understand what you're trying to shade so that you know what to enter for the lower and the upper. Okay. So mean is 72, sigma is 4.5. Okay. So we need to find the probability that the school male, high school male, the X, is shorter than 64 inches. So it's less than 64, right? So 64 must be this side, and shorter would mean less than 65, which is to the left of 65. Okay. So this is a cumulative area from the left, which means if you are doing it manually, if you found the corresponding z value for 64, then you can use that directly to get the table value. The body of the table will give you the area, and you can get your answer right away manually. So now for the calculator, you have to give a range of values, meaning in the previous example, we had a left end value, right? We had 80 and then we had 90. So the lower value was 80, the upper value was 90. The previous example too, we had lower and upper values, right? 15 and 30. But here, what will be my lowest value? It's kind of hard because you really can't tell what this end point is because it's actually going towards negative infinity. So I can't mark it as negative infinity. It's a value that's going towards negative infinity. And so it's negative infinity all the way to 64. So if you were to use your calculator on this one, again second bars, normal CDF, the lower value must be really, really, really small number. So what we suggest is, just put negative and a bunch of nines, because you're making it a large number but with a negative value, therefore negative sign, therefore the value is really, really, really small. Okay, so then as many zeros as it will accommodate, sorry, did I say zeros? As many nines as it can accommodate. So negative with a list of nines, and upper would be the 64, right? Because you're going from this leftmost end to 64. This negative infinity is what you're representing by using a numerical sense. This is nowhere close to negative infinity, so you understand that. We're just trying to keep it to the limits of the calculator. So we've got the upper limit to be 64, and then your mean will be 72, and sigma is 4.5. Enter that, hit paste, and your answer comes out to be probability of x less than 64 is, let me approximate it already, 0.0377. Okay, so the probability that a high school male is shorter than 64 inches is roughly 3.7%. So there's a 3.7% chance that a high school male is shorter than 64 inches. Alright, now what happens if you were to do it the other way around? Okay, so in other words, if I can quickly take you here. So what if you were given all these details and you were supposed to go up there? Okay. Meaning you have to find what that value is, if it's 80 to 90 or if it's exactly 80 and so on. Okay, so we're going in the reverse order. So the inverse of normal, we're trying to do the inverse of normal. So let's take a look at the next example. We're sticking to the high school male example, but we're changing it. Suppose the heights of high school age males are normally distributed with a mean of 72 and standard deviation 4.5. What is the maximum height of a high school male shorter than 80% of the distribution? Okay, so they're asking what is the maximum height. So maximum height means I have to give it in terms of inches, right? I can't give a z-score, I can't give a probability. They're not asking for that, but they've indirectly given us the probability. So they're asking us what is the maximum height. Okay. So to illustrate this, let's draw the graph. And this is your mean is 72 and sigma is 4.5. The mean is right in the middle, right? Your distribution is symmetric. We've established that if it's a normal distribution, symmetric properties hold true. So the left half of the distribution is 50%, right half is 50%, right? So they're asking what is the maximum height of a high school male shorter than 80% of the distribution. So we can say if this whole thing is 50%, right? This whole thing is 50%. That means if I need just a little more from this side, right, to make it 80%. So I am going to shade it a little more here. I can't shade the entire region. That will make it 100%. So I want only 80%. So this area is 80%. Okay. So for probability's sake, we're going to write this as 0.8 probability. So our question is, what is that value here? Where does that blue line end? Because that will be the maximum height below which high school males that are shorter than 80% of the distribution, right, would be below that. That would represent the lower 80% of the distribution, and that's kind of the mark that separates the lower 80 from the upper 20%, right? So we're trying to locate that position. So we know it's going to be more than 72. Is it 73, 75, 77, or is it some decimal value because it's continuous, right? Is it 74.32? What is it? So that is what we're trying to do. We're doing the reverse of it. They've given us the area and we're trying to find the x value. Previously we were given the x value and we tried to find the area. All right. For this, let's if we were to do this manually, then it'll be, you can still do it, but it's going to be correspondingly little challenging because you have to now go from the z-scale conversion and all that. So we'll go ahead and do this using the calculator. Okay, so for this we use the inverse normal key. Inverse normal. Okay, so for that we go to second vars, and then if you go down to, of course, the distur, and then you have the third option which says inv norm and open parentheses. So use that, of course hit enter there, and it opens to this new screen, inv norm screen, which says area, and so we know the area is 80%, which is 0.8, enter 0.8, and then it says mu is 72, enter 72, and sigma is 4.5, so enter 4.5 and hit enter, and that gives you basically your x value, right? It doesn't say x equals, but we know that we are trying to find the x value, so x equals 75.78729, etc. But remember, these are inches. They've rounded it to only one decimal place here, so then I will say x is 75.8. So that is the value, that is the height. 75.8 inches is the height, the maximum height that separates the lower 80% from the upper 20%. Does that make sense? So we are able to find that border line, that value that separates these two. And obviously this happened instantly for us. We'll have to come back and use the same language. What is the maximum height? So we'll say the maximum height is 75.8 inches because we need to give the units. Which represents what do I say? The border line that separates the lower 80% from the upper 20%. Okay. All right. Well, I couldn't help but come back to quickly show you how to do it manually so that you have the appreciation of how to go in the reverse or the inverse direction. Maybe I'll pull this down here. Oh no, I can just squeeze it here. Okay, so now we have area is 0.8, so probability is given to us, right? So I want you to go to the body of the table. So this is the body of the table, right, with all the probability, the area values. So you're looking for 0.8 here because the area is given to us. Now these are really too small, so let's go over here and locate 0.8. You're not going to find exactly 0.8 in the body of the table, but try to get as close as you can. So there's 0.79955 and there's 0.8023. Remember, if it was a calculator, you'll have a string of decimal values, but here we only have 5. So 0.80234. Okay, so that's the closest we have for 0.8. And look at the corresponding value for it. 0.80234 has 0.8 here and 0.05. So basically your z-score for the corresponding p-value is 0.85. So let's come over here and I'll say the z-score for what was it again? 80234. So this is the closest to 0.8 that we have. Okay. Is 0.8 and a 5, so 8.85 is 0.85. Okay, So now your z is 0.85, your mu is 72, and sigma is 4.5. So you're going to do the reverse, right? We're not going from x to z, we're going to go from z to x. So the x to z, the z to x conversion is, given z, how do you find x? So x is mu plus z sigma, right? And so come back here and enter mu as 72 plus 0.85 for z times 4.5. Okay. And then, of course, use your calculator to compute this. And that gives us 75.825. Isn't that neat? So when you round it, it comes back to 75.8. So it's not so cumbersome. It just needs assistance from the z table and work backwards. Okay. So we got the same value when we did it manually, but the calculator made it a whole lot easier for us. Okay. Now I want to take you back to one of the problems we did, the high school problem, where we found probability of x less than 64. I just want to keep the same problem and play around with another alternative. What if we were asked to find p of x greater than 64? I'm going to use the same graph, but I just want to show you that that would make it this blue region, right? If you were to find the blue region, how would you find that using the calculator? If you're doing it manually, you'll have to do 1 minus the yellow region. Okay. So the way we approach this is that the lower value, the leftmost end of your blue shaded region starts at 64. So your lower will be 64, but your upper goes all the way up to infinity, right? So for infinity, manually, if you want to represent as a very large number, again, throw a bunch of 9s for the upper value, right? For negative infinity, we did negative and a bunch of 9s. Here it is a positive with bunch of 9s. And of course, your mu, 72, sigma is 4.5. Go ahead and compute this. Okay. Typically, you will expect your probability to be really high, right? Because you've shaded a huge area. So it has to be really, really large. Now, for instance, the yellow region was only 0.03. So you should expect something in the 90, something at least above 96 or 95. So actually, when you compute this using the second bar's normal CDF, you get 0.9623. I rounded it to the fourth decimal place. So 96.23%. So that makes perfect sense that the blue shaded region was that. So this is how you will play around your calculator when you are trying to enter the lower value and the upper value, and when you don't have specific values, if they are tending towards negative infinity or positive infinity, this is the workaround for it. Now we have binomial distribution. Is it possible to approximate a binomial to a normal? What are the challenges? First of all, your binomial is discrete, meaning it jumps from whole number to whole number, and your normal is continuous. So there is no break or gap, there is a complete sweep of values. So we have some challenges when we have to do the conversion, but it is possible to get to approximate a binomial distribution to a normal distribution. It will come in really handy when there are some experiments that are done that fall under the binomial distribution setup, but its uses are more defined or refined, I should say, when we approximate it to a normal. So in order to qualify for a normal distribution, we have to understand, first of all, that binomial would be x with n, binomial with n comma p, right? And normal would be a variable x with normal mu comma sigma. So how do we patch between the np and the mu and the sigma? Okay, so first of all, there are two conditions, okay, requirements. The first requirement says that if n is large, NP must be greater than or equal to 5. And the second condition is NQ, or 1 minus P. They don't use the Q as much because they're all indirectly coming from P. So if N is large, that's where it matters. That's when you really want to approximate, right? If it's small, it's manageable, because a binomial table is very limiting. We didn't use a manual table, but you do have a manual table, a binomial table. And because that is very limiting, we find that approximating it to a normal distribution allows for the distribution to be more refined and be able to accommodate more values. And that's possible only if your N is large. In fact, I can show you a binomial table. It's a little grainy because I've really tried to accommodate a lot of values here. What you'll see here is that in this table, these are pre-calculated probability values. Now, the striking difficulty we notice here is, let me take my highlighter. You see the N value? That means you have up to 8 here. N equals 8 trials. So like this, we have the table that goes up to 20 for every value, and after that it jumps by tens. Then after the 20, N is 30. You don't have anything for 22, 25 in some tables. Some tables do figure that out and show that. But what I'm saying is you have that limitation. K is the number of successes, right? So if you had, depending on your N, the number of successes will increase, right? Because you can have up to N as a number of successes. And probability, P, this is the probability. Now, again we have jumps because we are going by some popular values, right? So because of all these limitations, if you come back here, that is the reason why we would really like to go with approximation. All right, so the approximation requires that we follow these two conditions, and if these two conditions are met, then the conversion would be that the mean will now be NP. Isn't that neat? This mean, and the mu is now connected with the N and the P, and then the sigma, which is the standard deviation, is now written as NP times 1 minus P, which is basically NPQ. Remember how we found this to be for the binomial distribution? This is what we did. But what we're saying is, when we have very large N, that very mean and standard deviation we found in the binomial distribution would become the mean and the standard deviation for the normal distribution. Okay, so I'll just say here, mean of binomial becomes mean of normal, and here standard deviation of binomial distribution becomes the standard deviation of normal. So now we are converting it to normal. However, there is one glitch here. We have to take care of that glitch, and we use a correction to fix it. Okay, now this is what we have. Now this is the normal distribution. We have converted a binomial to normal. Okay, now let's say there was a value, let's say 70. Okay, so if I say all values less than 70, right? What is the probability of all values less than 70? Say something like this. If it was a normal distribution, we would just shade this region, right? We would just get all of this and say, okay, less than 70. This would all be covered. But with binomial, what happens is, if we say less than 70, with binomial, the next number below 70 would be 69. There won't be any decimal values in between, right? So what happens is, when I say less than 70, I am losing the values in between 69 and 70. Therefore, what we do is, there is something called correction, where we continuity correction, where we try to, if it's less than 70, we have that difficulty. If we want to do less than or equal to 70, then it's fine because 70 is included and everything less than that. So instead of starting at 70, we will say find the probability of x less than 70.5. So the continuity correction would be fixing it, half a point up or half a point down. Okay, so we take the x value and we do plus or minus 0.5 for continuity correction. So we could do that, or we could do less than half a point away from 70, which would be 69.5. Now think about this. To represent p, a probability of x less than 70, which one should I use to make sure that we're taking values less than 70? So you know that the normal distribution will take the 70 into consideration. So what we have to do is we have to go with x less than 69.5 so that we have 70 not included. If I wanted probability of x less than or equal to 70, then which one should I use? 70.5 or probability of x less than 69.5? I want to include 70, right? So I go a little above 70 so that below that, because there's no 70.5 in a discrete situation, there is only a 70 and then a 71. So this 0.5 adjustment does not include any new values, but it helps you to include or exclude the border value. So here we have to use 70.5. So all values less than 70.5 would include 70 and all that's below 70. Okay, so that is how we use the continuity correction. Now let's take a look at an example and see how we go about it. At a university, 30% of the incoming freshmen elect to enroll in a statistics course offered by the university. Approximating the binomial distribution with a normal distribution, find the probability that of 600 randomly selected incoming freshmen, at least 200 have elected to enroll in the course. Okay, they gave us some details about how they want us to approximate the binomial distribution to the normal distribution. Okay, so let's try to figure out what we have here. Now we are told that x is binomial n comma p. So what is n? N is 600, right? So we are told that we have now 600, and p, probability is how the whole idea is how many enrolled in the statistics course. So we have only two options: those who enrolled in the stats, those who didn't. So that's 30%, which is 0.3. So I've got this. We have to convert this to x normal mu comma sigma, right? And so and not just that, we have to find the probability for that last statement. We'll come to that. Now in order to make sure that this approximation is valid, we have to check the requirements. Okay, now our n is really large. There is no binomial. I mean, with the calculator, well, maybe we can find that, but it is we don't have it in the tables. So that was the reason why this first came to be utilized, because the scientists, the mathematicians, statisticians couldn't handle high n in a binomial situation, so they found the way to make this approximation. So the first one is np must be greater than or equal to 5. So let's multiply. 600 times 0.3 is 180, which is definitely greater than or equal to 5. We got that. And the second condition was n times 1 minus p should be greater than or equal to 5. So 600 times 1 minus 0.3, which is 0.7, is 420, which is greater than or equal to 5. Since they both are greater than 5, this implies that we can approximate binomial to normal. And if that's the case, we have to understand that we are asked to find what's the probability of at least 200 who have elected to enroll in the course. Probability of at least 200 means 200 or more. So greater than or equal to 200, right? Probability of greater than or equal to 200. Now, because of the continuity correction, I'll just say continuity we have to adjust this, okay? So let me give you the context again. Now this time we have, I don't know, I'm just going to mark 200 here. Okay, so we want greater than or equal to 200. We want to include the 200. So it's this region. If I want to include 200 in the discrete setup, the number before 200 will be 199, right? So for continuity correction, you go half a point away, you add or you reduce. So my question is, we know we're going to do that continuity correction. So will it be 199.5, half a point below, or 200.5? So are we going to rewrite this as probability of x greater than or equal to 200.5, or should we say x is greater than or equal to 199.5? Which one of these will include the 200, because we want the 200? So clearly if you went below, then you know that 200 will be included because of the discrete setup. So we have to go with probability of x greater than or equal to 199.5. So if you're using the calculator, you know your end point, the lower limit, the lower value will be 199.5, and for the higher one, you're going to go with a bunch of 9s. We've got that. But what will you enter for the mu and the sigma? So for that, you know our mu is now n times p. That's part of the formula. So that's going to be 600 times 0.3, which is 180. And sigma is square root of npq. If you want, you can calculate all these here beforehand, or you could punch them all into the calculator directly, so that it'll take care of that computing as well. So this is 0.3, and that's q is 1 minus 0.3, which is 0.7. Right? So you can compute that and enter those values too. Okay. So I'm going to try and keep it as it is and compute it, punch it in there. Okay. So go ahead and get to normal CDF. So you have to do the second vars, normal CDF, which is the second option, and then go there and enter your lower limit to be 199.5, right? That's the lower one. So we start a little ahead, and then we have all the way up to a bunch of 9s. And then mu, you can enter it as 600 times 0.3, or you could enter the value that we have, and this would be square root of 600 times 0.3 times 0.7 and close parentheses, then paste, and that gives you, without much without any inconvenience, you get probability of x greater than or equal to 200. Upon adjustment here in the binomial setup was probability of x greater than or equal to 199.5, and what you did there was the normal CDF. The lower limit was 199.5, upper limit was a bunch of 9s, and we entered the mu as 600 times 0.3, and I entered the standard deviation simply as 600 times 0.3 times 0.7. When you do all this, it's convenient, but you have to be very careful about how to enter it mathematically. The square root should be for everything, so the whole thing should be under the square root. Remember to close the parentheses, and remember to use the multiplication all under the radical sign. If you did all that, your answer should come out to be 0.0411760672. This is what I get, and of course you can round this to 4 decimal places, 0.0412. So the probability that at least 200 incoming freshmen have elected to enroll in the statistics course is 4%. The probability that your local ice cream shop is out of your favorite flavor on any given day is 15%. Hoping to increase your odds of getting your favorite flavor, you visit the shop 100 times in 6 months. What is the probability that you will get your favorite flavor less than 40 times? Oh, you must really, really love that flavor. All right, now we have, again, binomial situation, right? Getting your favorite flavor or not. So if I think in terms of binomial, my n will be 100 because you repeated that experiment, that trial 100 times. P is the probability of the shop going out of your flavor. That's the success here. Running out of your flavor is the success, which is 0.15. Okay. And let's do the quick check. And P is 100 times 0.15, which is 15. So we're good there. And n times 1 minus P. When I say it's good because it's greater than or equal to 5. So let me put that there. Meaning the requirement is satisfied. 1 minus 0.15, which is 85, is also greater than or equal to 5. So we're good with those two conditions. We can convert from binomial. We can approximate the binomial to a normal. So mu will be NP, which is 100. It's just a coincidence in the sense that your mean formula and the requirement seem to be the same. So so it's kind of convenient that you have the calculations already, right? But we're going to use you can enter it as it is in your calculator, so you don't have to worry too much about this. 100 times 0.15 times 1 minus 0.15. Okay, so you'll enter all these things in your calculator, but let's quickly do the probability. So the probability, what is the probability that you'll get your favorite flavor less than 40 times? So X is less than 40. Now again, remember the continuity correction, right? You want it to be strictly less than 40. You do not want to include 40. So if you were to graph this, again, I don't know where the 40 will be because oh yes, I have the mean, so that will help me here. So mean is 15, so 40 is somewhere here, right? So less than 40. Less than 40 again would be this region. But with a continuity correction, my question is, if I want it to be strictly less than 40, do I do 39.5, less than 39.5, or should I do less than 40.5? So think about this. You do not want to include 40. So if you went above 40, if you said X less than 40.5, you will include 40. You don't want that. So you want to go a little below 40, and so you'll set it at P of X less than 39.5. For continuity correction. And this is going to change the answer, so you have to be pretty clear about what we're doing here, okay? So that it does not include 40 due to the strict inequality. That's it. Now go to normal CDF. You know how to get to that. And now this is the yellow shaded region, so you start from the leftmost end. The lower limit is negative infinity, so do negative and a bunch of 9s. And the upper limit will now end at 39.5. It will not stop at 40, right? Otherwise 40 will be included. Your mean, we figured that to be 15, so I'm going to put that as 15. Now you can enter the sigma as it is, or if you have it calculated like I have here, you can enter that as well. So anyways, doesn't matter what you entered, those values should come out to be the same. So what you do is now of course hit enter and see what answer you get. And interestingly, your answer comes out to be 1 in the calculator, right? It gives you what does probability equal to 1 mean? It means it's absolutely certain, right? So it's absolutely certain. So the probability that the ice cream shop has your favorite flavor less than 40 times is absolutely certain. Okay, so I find that really funny that you go, the person visits 100 times just to be sure, but in 6 months. But this is the chance. There's a 100% chance that you will get your favorite flavor less than 40 times. Okay. All right, class. So, well, with that, we end up on chapter 6. And this again has not been too bad. We just had one lecture. These are all, long lectures, but they finish in one lecture instead of several parts to that particular chapter, especially with chapters 2 and 3. They were long. We also have some upcoming chapters that are long, but these ones have been good. So good for us. And thank you again for watching this video. I hope you enjoyed it. And I will see you in chapter 7 next time. Bye.